Hi, in this video we'll talk about the Cochrane-Orcutt test for trend. Recall the issue that we have. It's a dilemma of when we look at a time series data set that seems to have a linear trend, whether it's increasing or decreasing. The difficulty is asking ourselves, is that really a trend that's going to extend forever? Or is that just a temporary pattern and later on we don't know when, maybe that trend is going to reverse and go the other direction or flatten out. So that's a really difficult problem, and it's going to cause us trouble if we miss on that question. And we've seen that if you were to look at a simple linear regression test, which remember what it does, if you check for the significance of the beta 1 coefficient, what you're doing is you're checking to see if that beta 1 coefficient equals 0. If you reject that beta 1 equals 0, what you're saying is that beta 1 is not 0, meaning that there must be a significant slope, meaning that you're concluding that there is a trend line that you're expecting to continue forever. And we have shown by simulations that that simple linear regression test, if you were to run that 1,000 times or a large number of times, it commonly rejects the null when it should not. Meaning that it falsely says, oh yes, there's a trend here that's going to last forever, when in reality, that's not the case. It's just a temporary set of time where the trend did seem to go upward, but really it was just a period of time where that was going to end at some point. So that's the problem that we have, and that's where we're at. Well, in 1949, two researchers named Cochrane and Orcutt came up with a method that would try to solve this issue of being able to detect a trend when there really is one, and being able to say there's not one when there's not one. And we'll talk about that right now. So the steps for the Cochrane-Orcutt test, they look very involved here, but really it's a lot of algebra. It's not going to be that complex. The steps for the Cochrane-Orcutt test are, first of all, we want to consider a line plus noise model. X sub t equals B0 plus B1t. There's our friendly line from long ago that you learned. Plus some z of t. Well, now that we've studied time series for a while, we're in chapter 8 now, we know what z of t is all about. Z of t satisfies the AR1 model, 1 minus phi1 b, that's operator b, and that's going to come into play quite a bit here. Operator b times zt equals at. So that's the form of the AR1 model. Okay, given that, then here's the Cochrane-Orcutt test. First of all, calculate the least squares estimates for this B0 and this B1 and name them beta hat 0, beta hat 1 to fit a linear regression line to the original data. So far, that's what you would do if you're just trying to fit some line to a set of data that you're calling linear. So at this point, we're not even thinking that we're in a time series setting. This is just part of the Cochrane-Orcutt test, though. Okay, well, given that, since we fit the B0 and B1 by this beta hat naught and beta hat 1, we can then calculate z hat t. So we have an estimate for these residual terms by simple algebra. Pull the b naught and b1t over to the other side, and we have xt minus b hat naught minus b hat 1t. And we've already said that we're assuming that that is approximately an AR1 because we had said that here. One thing I want to mention, there's nothing crucial about it being an AR1. It could have been an AR2 or an AR5, so we'll just call it an ARP. But for this discussion, we'll just assume it's an AR1. So we have this z hat t that is approximately AR1. Well, it makes sense then that we would go ahead and fit an AR1 model to that z hat t, which is a common thing we do. What will that do for us? That will allow us to get an estimate for this phi 1. So we now have phi hat 1 because we have fit an AR1 model. to the residuals. And then at this point, step 4, the last step, we will compute this new variable. It's a transformation. Y hat t equals 1 minus phi 1 hat operator b times xt, where t equals 2, 3, 4, so on, all the way out to n. I can understand if 1 looks to be strangely missing, but think about why that would be. 1 is missing because this operator b says we're looking at xt minus 1, and if t equals 1, then if you look one step back behind that, that's t of 0, and we don't have a data point there. So we start at 2. So here we are with this y hat t of given by this. Now, if you just look at that, my first thought is, well, I don't know what good that did me, but okay, fine, I'll do that. Well, here's the key. This is why this method works. Notice that starting at this line right here, if y hat t equals this, we know that xt was given by first line here, b0 plus b1t plus zt. Substitute that in, and let's see where that takes us. Do some algebra, we'll do some distributing, and we will distribute this 1 minus phi 1 operator b with the b0 plus b1t, and then distribute the 1 minus phi 1 operator b with the zt. And then let's use FOIL on this first product here that has 2 terms in it each, so we can use FOIL, and so we get b0 plus b1t. That was just simply by multiplying by 1, and then minus phi 1 hat times operator b times b naught. That just simplifies into minus phi hat 1 times b naught. Why is that true? Because operator b on a constant is just the constant. So that's why this turns into minus phi 1 hat b naught. Minus, here's the last term in FOIL, minus phi hat 1 operator b times little b1t. And that turns out to be the following. The minus phi hat 1 comes across. Operator b on b1 is just b1. Operator b on t is t minus 1. So that's why this term looks like it does. Plus, copy this final term from above of 1 minus phi 1 operator b times zt. Okay, well, still, we could look at that and say, I'm not sure why that's the key, but let's look a little closer. We can collect like terms and rewrite our y hat t as, let's collect the b naught terms. Notice we've got a b naught here and a b naught here. So we can pull out the b naught and say 1 minus phi hat 1. Then let's go do the same thing with b1. We've got a b1 term here and a b1 term here. Pull out the b1 and multiply by t minus phi hat 1 times t minus 1. And then copy our final term from above. And we'll rewrite that as a c for constant. So we're saying that this piece right here is c, plus b1 times, we'll call this t minus phi 1 times t minus 1, just t of phi hat 1, plus this term that we'll call gt. And remember that this was the term that was the AR1 model. Well, where does this take us? And we will look at this on the next light board and talk about why the key is right here, and this is why the Cochrane-Orcutt method works. We'll be back in just a minute. Okay, let's continue where we left off. And remember what we had done. We had looked at this y hat t and written it in a pretty strange looking way, I'll admit. And I said that this is going to be a better situation for us. So let's talk about why why this is a better situation than what we had before. Y hat t we wrote as we turned this first term into the constant. We then said we've got a b1 here, and we called this t term t of phi hat 1 plus gt, where gt is this piece right here. That's going to be a super important piece as we go on. Let's look at this in more detail. C is just a constant, and it has changed from what we originally had, but that's not going to matter because when we're testing for trend, that's the slope term, so we don't care about the constant term anyway. Now here is that trend term b1, the slope. Notice that the slope is still b1 just like it was before. That has not changed. So our slope is unchanged, but our time term has changed. It's different. That's why we've labeled it differently here. Looks like this. And then plus this gt. Now, what is GT? Well, that, of course, sounds like this piece right here. It sounds like our residuals from the last model, right? And remember that this residual ZT term is really what threw the SLR test off, because remember, those residuals were correlated. Well, because they were correlated, that's what caused the model all kinds of trouble and made it reject the null when it shouldn't have. So it appears that we've got that same issue, but I'm going to show you that we actually don't. Here's why. Remember the original AR1 model, 1 minus phi1 operator b times zt equals at. Well, because of that, we could solve for zt because we could invert this by multiplying by 1 minus phi1 b inverse, and that would give us zt. That would give us zt equals 1 minus phi1 operator b inverse times at. Then I can substitute that in here. Remember, g of t, gt equals 1 minus phi1 b times zt. So we copy our 1 minus phi1 b. We've got a new name for zt. It looks like this. It's 1 minus phi1 b inverse at, not phi1 hat, but phi1. So I substitute that in here, and I now have 1 minus phi1 hat b times 1 minus phi1 b inverse at. If you just look at that, glance at it quickly, you may think, oh, those are the same things. That should multiply out to 1, or the identity. But it's not true, because this is phi1 hat, this is phi1. But they should be close, because phi1 hat is an estimate of phi1. So that's what we mean when we say they nearly cancel out. They nearly cancel out because phi1 hat is an estimate of phi1. So those nearly cancel out to just be 1, leaving us with at. Well, that says then that gt is approximately at. But remember that at is assumed to be correlated. It's to be uncorrelated. That should be is uncorrelated. Therefore, so is g of t uncorrelated. And that is quite an improvement over what we had when we started, because we knew that the z of t was correlated. But we've made a transformation that has made this uncorrelated. And now what? What good does that do us? Well, now we're back to original methods, standard methods, and that is the SLR, simple linear regression methods, where you can test for the B1 coefficient. The null is B1 equals 0. The alternative is that it doesn't equal 0. Your test statistic is the same test statistic that it has been in the past for the standard linear regression. We'll put a CO up here. That's what we did in our text for Cochrane-Orcutt. But it's really the same test that we've had in the past. And now, if we reject the null, we feel like there's a much better chance that we should have rejected the null. And we did that. We looked at simulations for the Cochrane-Orcutt test, and they were much improved over the SLR tests that we had shown previously. So this is the Cochrane-Orcutt method, and I hope that makes it more clear. It looks pretty daunting the first time through, but if you take another look at this, you'll realize that really it's a lot of algebra, and the idea of theirs was quite clever, and this was one way to get around the correlated errors, was to make a transformation and make it something that's uncorrelated, and then proceed with the standard SLR test.